Okay, so looking again at the information we put together in the previous video, we're trying to figure out at the actual equivalence point of a titration of 50 mils of a weak acid, acetic acid, with a strong base, and they're equal molar amounts. So I'm going to set up an initial equation, a rice table, and I kind of call this one like a titration rice table. In other words, they're not going to really have an equilibrium directly out of this one. I just want to kind of use this to organize information. So based upon the stuff that I have to begin with, I have 50 mils of this concentration. If I multiply those two, volume in liters times the concentration, 0.1 molarity, I will have 5.0 times 10 to the negative 3, and these are moles. I didn't leave myself a lot of room. So those are moles. I have an equal amount because it's at the equivalence point. Remember, at the equivalence point, they're equal moles amount. Initially, I don't have any of this, and I don't have any of this. Now, at the equivalence point, remember, OH goes to completion. So both of these are going to be minus that amount. This will be gone, minus this amount. And again, this is gone. I'm not going to write moles. So it's gone 100%. And that is equally added to the base, conjugate base. And there it is. So at the end of the titration, at the equivalence point, both of these species are 100% gone, and all of it is transferred over to the base. And I forget, I did this incorrectly. I put OH over here, and you're probably screaming about it the whole time, but I'm seeing it now. This is water, and I really don't care about it. So again, this takes a hydrogen from here and it puts it over there, so water. Okay, so this is important stuff here. So it's like, well, what's going on? We talked about the equivalence point, I don't see anything. Exactly, you don't see anything. We have to do a second part, which is going to actually create the equilibrium. And it's going to be a little bit screwy. Now remember, these are moles. We'll come back around to that in just a moment. You may think this is tedious, and you're not wrong. But we kind of need to do this to organize the information. Now, this is what was remaining at the end of the titration, the conjugate base. Here it is. We're sitting here reacting with water. Water, again, I'm not concerned about. And it will form an equilibrium because it's a conjugate base of weak acid. It's going to mix and it's going to have some balance between itself and the original weak acid. Don't forget, all of this we're talking about acetic acid and sodium acetate. And now here is the OH that comes into play because this is going to take a hydrogen from water and give you this. Okay, I am now, because I'm not doing any mixing of things, this is just sitting here with water and it's going to react with water and take a hydrogen. So I can now switch this over to total volume molarity. So over here, I'm just going to do some scratch work. 5.0 times 10 to the negative 3 moles of the sodium acetate divided by 0.1, threw myself off here with that very dramatic line. 0.1 liters, that is the sum total of the two 50 mils. So 50 mils and 50 mils. I don't know if I stated that directly, but that is the volumes that we had for these because, of course, they're the same concentration. It would require the same volume. So the total volume would be 100 milliliters or 0.1 liters. If I divide this out here, I will be left with 5.0 times 10 to the negative 2 molarity. And starting off with these guys, I don't have any. But as I go through the process again, this is going to go down by some amount, but it's kind of close to that same amount. And these are going to go up by some amount, which I want to know. And there it is. Okay, so just like before, we can set this thing up as far as products over reactants, but I don't have the initial K value. I have what's acetic acid. I have a Ka value, and that happens to be equal to 1.8 times 10 to negative 5. I need, because I'm dealing with the base and only the base, I need a Kb value. And the Kb value is equal to Kw divided by Ka. So if I divide 1 times 10 to negative 14 by this value, that's going to be equal to 5.6 times 10 to negative 10. And I can just go ahead and do this problem now. 5.6 times 10 to negative 10 is equal to x squared over 5.6. No, not 5.6. 5.0 times 10 to negative 2. Go ahead and solve for x. X will equal 5.29 times 10 to negative 6, and that happens to be equal to the hydroxide ion concentration, which is pretty darn close to where we want to go. We want pH. If I go ahead and do the negative log of this thing, the pOH will be 5.28, and my pH, subtraction from 14, will be 8.72. And there you have it. Problem done. So yeah, a little bit tricky. Okay, let's get rid of this, and we'll start another small section, but this is going to be right out of your homework, number 37. And this is going to be a reasoning through type problem. And we're definitely going to have to work through this together because it's a little bit tricky. First one, predict whether the equivalence point of each of the following titrations is below, above, or at a pH of 7. Okay. First one, the titration of sodium bicarbonate titrated with NaOH. A little tricky. Sodium bicarbonate or bicarbonate, that is something that is amphoteric, meaning it can go and lose a hydrogen or gain a hydrogen. It's somewhere in the middle. You probably learned this in like biology or something. But in this particular case, it's reacting with a very strong base, and that strong base is going to take the hydrogen. So we'll go ahead and just write an equation just so we can see this. It's a one-way direction, and what you are left with, I'll go ahead and write the water first, and carbonate. So the thing to think about here is at the end of this reaction, what do you really have? Carbonate. What is carbonate acting as? An acid or a base or like a salt doing nothing? If you said base, you are right. So this is acting as a base. That is the only thing you have left in solution. Now it is going to go back in the other direction when this is the only thing. We just did that example problem. This will react with water. So forget about this equation. I'm just going to focus on this. These two guys are sitting in water. This is going to react with water and form some of these two guys in a small, appreciable amount, just a little bit. Really, this is my simple question. If you have this in solution, it is a base. Where do you think the pH should be? Well, if I have a base in water, I would expect it to be basic. So therefore, it should be something greater than 7. As everything we just stated, the base is going to react with water, take a hydrogen, it's going to create some hydroxides, basic solution. Got it. Okay, next question here is you have some ammonia and it's titrated with a strong acid. So we'll do the same thing just so we can see it. You got some NH3. I don't care about the Cl. I only care about this part. And it gives me the conjugate acid, ammonium, and, well, that's it, actually. I'm trying to write something else in here, and it's like, what am I supposed to write? Nothing. So given this scenario, this goes 100% to completion. This is a weak base. This is the conjugate acid weak base. The only thing remaining in solution, and I am at, again, the equivalence point. So if this is the only thing remaining in solution, this conjugate acid, it's an acid. So therefore, I would expect my pH to be something less than 7 because it's going to be an acid and it's going to give that hydrogen to water and create some hydronium ion. So it should be something less than 7. The last one on this list, KOH plus HBr, really what this breaks down to is OH minus plus H plus. And these guys will go to completion and create some water. So if you have some water in an aqueous solution, picture that, where would I expect the pH to be? I would imagine this is simply going to be equal to 7. So these 3 questions are really good AP style questions because there's no real math involved, but you have to kind of think about how things react with each other and what they will do at the end of that reaction. Again, really good question, so you should pay attention to this kind of style because it's a nice one that we can throw at you and see what you know. Okay, end of lecture.